Welcome to The Explainer. Today, we're exploring a truly fascinating collision between biology and swarm robotics. What actually happens when you combine the frantic survival tactics of tiny insects with cutting-edge autonomous algorithms? Well, let's dive right in and find out. Think about this for a second. How do you get a swarm of completely independent robots to agree on just one thing? In a standard computer network, you've got a central server, right? A leader giving orders. But in swarm robotics, there is no leader. You literally have dozens, maybe hundreds of autonomous agents out in the field. If they suddenly need to regroup at an optimal location, how on earth do they collectively decide where to go when nobody's actually in charge? In the robotics world, this is formally known as the best of N problem. It's a massive collective decision-making challenge. Basically, decentralized agents have to evaluate multiple candidate solutions, like, say, several different gathering spots, and somehow converge on the absolute best one. And here's the real kicker. They have to do this using only local communication. They can't just broadcast a text message to the whole swarm. They can only talk to the robot standing immediately next to them. It's a huge hurdle. Historically, engineers have tried two main approaches here. First up is the value-sensitive approach, which is inspired by honeybees. When scout bees find new hives, they communicate by doing those little waggle dances. It's fast and it relies entirely on local communication. But it's incredibly risky. If two candidate spots are super similar, the swarm can literally split right in half. On the flip side, we've got the value-free approach. This one is modeled on human majority rule voting. It's safe and it's absolutely guaranteed to eventually find majority support. But the glaring limitation? It requires every single agent to know the overall group opinion. That demands complex global communication networks that, frankly, robotic swarms just don't have. Section 1. Inspiration from rock ants. Nature's surprisingly simple solution. Enter our star of the show, the rock ant. These guys nest in extremely fragile rock crevices and live under a massive amount of stress. They're forced into frequent, urgent migrations, which presents a huge problem because an individual rock ant has a brain about the size of a pinhead. They simply aren't smart enough to visit nest A, then go visit nest B, and consciously compare the two. Yet, despite being simple and nearly blind to the big picture, they have to move as a completely unified group, or they'll die. So how do they pull this off? The secret lies in something called a response threshold variance system. Now, that sounds incredibly complex, but it basically just means that individual ants have different naturally distributed levels of sensitivity. Think of it like a group of friends trying to pick a restaurant. Some have super low standards and will gladly eat anywhere, right? While others are incredibly picky and will only settle for a 5-star meal. Well, in the ant world, this variance forms a normal bell curve distribution. Some ants will accept almost any new nest, while others will reject literally everything except the perfect crevice. This natural diversity is actually the foundation of their collective intelligence. Section 2. The consensus algorithm, translating ant behavior into robotic code. To turn this into code, an active robotic agent, or an ant if you will, follows a really elegant 3-step loop. Step 1, evaluate a candidate nest. Step 2, perform a quorum check to see how many others are already there. And Step 3, decide whether to recruit a peer or physically transport a passive agent to the new site. Let's break those mechanics down a bit further. When an active agent finds a nest, it asks itself a simple question. Is the quality of this spot higher than my specific pre-programmed threshold? If the answer is yes, it approves the candidate. Next, it looks around for that quorum check. Are there enough other active agents already hanging out here? If the quorum is not met, the agent runs back to the old nest and initiates tandem running. This means it physically leads one other active agent to the new site to help build momentum. But if the quorum is met, meaning a critical mass of agents already agree this place is great, the agent switches gears into transport mode. It starts carrying the passive agents over. Just like that, the migration has officially begun. Section 3. Preventing swarm division. How to deal with stubborn agents and bad choices. Okay, so to prevent the swarm from just splitting up forever, the algorithm uses a brilliant failsafe called the majority syncing bias. Remember those incredibly picky agents we talked about, the ones with high thresholds that reject almost everything? Well, if they visit a candidate nest and reject it based on its quality, but then look around and realize a massive crowd of their peers are already gathering there, this bias kicks in and overrides their initial rejection. Basically, if the number of agents present exceeds a certain mathematical limit, the stubborn agent concedes. It's essentially saying, look, I don't love this nest, but since everyone else is here, I'm in. This guarantees the swarm ultimately converges. But wait, what if that crowd is gathering at a totally terrible nest because a bunch of easy-to-please agents approved a bad option early on? Enter reverse tandem running. When a highly sensitive, picky agent investigates a poor nest and rejects it, it doesn't just walk away in disgust. If it sees other agents lingering there, it will literally drag them away. It initiates a reverse run, actively pulling those mistaken agents back to the old nest. This actively dismantles bad decisions before they can ever reach that critical quorum limit. It's a fantastic self-correction mechanism. Now, evaluating a nest isn't just about one single metric. Nests have different sizes, different sunlight levels, and different drainage qualities. If every single agent had completely random thresholds for all of these things at once, the swarm would be wildly inefficient. So researchers introduced the multi-lineage model. They programmed the robotic swarm in fractions. For instance, one slice of the swarm, lineage A, is specifically sensitive to size. Lineage B is highly sensitive to sunlight, and lineage C focuses entirely on drainage. By mixing these lineages together, the algorithm ensures the swarm as a collective body is fiercely evaluating every single complex environmental factor, even though each individual agent is only really paying attention to one specific thing. Section 4. Simulations and UAV Applications, Testing the Algorithm and Looking to the Future. So the theory sounds beautiful, right? But does it actually work when put to the test? In a simulated environment, researchers introduced an old nest, one good nest, and two highly deceptive poor nests, and they made the parameters incredibly tricky. The good nest got perfect scores of 6 across size, sunlight, and drainage, but poor 1 and poor 2 scored 6s in 2 of those categories and dropped just a single point to a 5 in the third. For simple robotic agents operating in a noisy environment, mistaking one of those poor nests for the good nest is incredibly easy to do. Honestly, a traditional algorithm would almost certainly split the swarm or get stuck in a total deadlock here. But using this rocket-inspired algorithm powered by that multi-lineage model, the results were absolutely staggering, a 100% success rate. In 500 separate trials, the agent swarm successfully rejected the deceptive core nests and migrated entirely to the good nest in every single trial, no exceptions. The combination of reverse tandem running tearing down the bad choices and majority cinching bias cementing the final good choice proved to be an utterly flawless decision-making engine. And the coolest part is this isn't just some academic exercise confined to a computer lab. This exact decentralized and inspired logic is bleeding into cutting-edge technology today. Just look at recent engineering research, like this paper on distributed double-loop optimization for UAV swarm scheduling. Researchers are actively looking at these methods to coordinate massive fleets of autonomous drones. When you have dozens of drones that need to schedule tasks, manage airspace, or evaluate target zones without a central command tower, you run into the exact same best of N problem that our tiny rock ants face every single day. By borrowing millions of years of evolutionary trial and error, we are bridging the gap between biology and artificial intelligence. If a colony of ants can schedule a seamless, perfectly synchronized migration under absolute duress, using nothing but local nudges and varying thresholds, what will our autonomous drone swarms conquer next? It's a thrilling frontier, and it all starts by just looking down at the ground beneath our feet. Thank you for joining me for this explainer. Keep your eyes open, because the solutions to our most complex technological problems might just be crawling right past you.